Good afternoon, Chang. Okay, at least you guys are 21 now. We are going to begin. First of all, good morning to you all. Sorry, good afternoon. It's past midday. Good afternoon.
Good afternoon.
Okay, I hope all of you are doing well. And
Yeah,
I hope you revised what we did yesterday and it's clear because we are going to advance. So yesterday we looked at the system de coordonnées Cartesian and system de coordonnées cylindrique. Okay, we defined the vector position, and we also tried to establish some expressions of transition when we're transitioning from one system, the coordinate, uh, to another system. So we had those expressions derived. We also looked at the system, the coordinate polaire, which is just more like system the coordinate cylindric, except that z is equal to 0, it's just in the horizontal plane. So today we are going to advance from there. We are going to try and look at the coordinate spheric. Then afterwards, we can try to begin le vecteur, vitesse, accélération, et tout ça. Yeah, so we'll look at the coordinate spheric. Sure, it won't be long. If you guys had revised what we did yesterday and made sure you understood it, I'm sure today's work is going to be relatively simple because we'll just be doing the same things we're doing yesterday. Maybe the expressions might be a bit longer and just a bit more complicated, but it's still going to be the same thing. We'll still be using the same principles of projection, same trigonometric principles, and all that. And as we defined yesterday when we began this chapter of Cinématique, we said we are going to be looking at, or we will be studying the movement of a point without taking into consideration the causes of that movement. So if we're going to be studying movements, it implies we are going to look at things like velocity, acceleration, and all that. So after we define the last system, the coordinate we're going to look at, which is the coordinate spheric, we are going to now try to calculate the vector vitesse, vector acceleration for all the system, the coordinate we have defined so far. So we'll get right into the coordinate spheric. Yesterday I told you guys that for coordinate cylindric, we use it for movements that are symmetric par rapport à un axe. They have an axis of symmetry. As we saw yesterday, the z-axis yesterday was the axis of symmetry. So if a point has a movement around that axis, it makes a cylindrical movement. The difference between that and what we will be looking at today is that this time, the symmetry is going to be around a point or par rapport à un point, as in the case of a sphere. A sphere has symmetry at its origin, the center, at its center. That means when you go to the center, you can make an infinite number of circles or of symmetry lines. As we all know, a sphere has an infinite number of symmetrical lines because its symmetry is at a point, meaning from that point you can define so many lines and you still have symmetry, as opposed to symmetry par rapport à un axe. So it just becomes obvious that the expressions in the coordinate spheric are going to be a bit more complicated, but not so very complicated, but just a bit more. We are going to advance a step further than we did yesterday. And as we will be doing the coordinate spheric, I would like you to imagine the Earth. We're going to use the Earth as the best example today. The Earth is composed of longitudes and latitudes. I'm sure you guys did that in geography. We all did geography in junior secondary. So picture the longitudes and latitudes, the lines of longitude and latitude, those lines. I'm sure you guys know what those circles or those lines represent in real life or in mathematical terms. Sure, we all did earth geometry in ordinary mathematics in high school. We must have dug deeper into longitudes and latitudes and what they represent. And even in geography, I remember we did that. Those longitudes and latitudes, what they are is They are just basically angles certain points on the earth form. So let's say you have your center, the center of the earth. I don't know where it's located, but we have the center of the earth. And then we have also the origin where we start from measuring those angles or those lines of longitude at zero. I think it's the prime meridian. It's the one that's at 0 degrees for longitude at prime meridian. You have that. So when you start advancing from the prime meridian, it's like you'll be forming angles from that line up to wherever you'll be. So for example, if you have a place located at 33 degrees, and that's the line of longitude there, 33 degrees, they're telling you it's located at 33 degrees. It means that place there, let's say we call it Lusaka, we imagine Lusaka is located at 33 degrees. We are going to say Lusaka is forms an angle of 33 degrees from the prime meridian, you know, the 0 degrees there. It forms an angle of 33 degrees, and that's what that line of longitude there represents. Same thing for the latitudes. We have, I think the equator is the one that's at 0 degrees, and you get other lines of latitude. So let's say we get a city like London, and we say its latitude is 45 degrees. That means London forms an angle on the Earth's surface there that we are studying of 45 degrees from the 0 degrees, the equator. So that's what those lines of longitude and latitude represent. And that's what we will be looking at today. It's not so obvious, but if you think about it, it's the same concepts. We'll be forming those same circles or those lines of longitude and latitude. We won't be calling them that here, but those are the things we will be studying. So one thing you have to note, first of all, is that l'étude de mouvement symétrique par rapport à un point. So it's symmetrical around a point. So like the Earth, its symmetry is at its center, the center of the Earth, wherever it's located, that's where the symmetry is. So we have this figure here to show us graphically what we are going to be looking at. And as you can see, you guys, there's a sphere here, and you can see some circles around the sphere. They are looking like lines of latitude. And you can see this one also a longitudinal line. And what these are telling us, or what these represent, is simply the angle, the point that we are studying forms from the center or from the origin. Exactly. But besides that, when we are studying imagine a plane flying in the sky. That plane is moving around, not around the Earth, but on the Earth, but around since the Earth forms a sphere. So it's like that plane is moving in that space formed by the sphere. So that plane is in some sort of way, it's forming a smaller sphere inside the Earth's sphere. And that sphere that plane forms, it has its radius. So from the center of the Earth, you can calculate the distance of that plane. So let's say the plane is flying at maybe 30 kilometers from the origin of the Earth. We can say that's the radius of the sphere that plane is forming, or the sphere, yes, the radius of the sphere that plane is forming in that space of the Earth it's flying around. So whenever we are trying to define the position of a point in the system, the coordinate spheric, we use the radius. Every point, when it's moving in a spherical manner, it forms a radius, because we all know that spheres, circles, and all those things, they have radii. We define them with their radii, their radius. Okay, so every point is going to form a radius. So if I am on this sphere and I know my point M is here, you can see that this point M is forming a radius, this radius there. Its distance from the origin, the center there, the distance from this point to that point there is its radius. So if you are asked, say, where's this point located? You say, where is the point M located in the space we are studying? We'll say, okay, it's at a radius of 30 kilometers from the center of the Earth. At least the person is going to know, oh, all right, so it's located here and there. So they form every point we are going to study that's moving in a spherical manner is going to form a radius. For it to be spherical, it just has to have a radius from the center. It's obvious, ça se voit, it's just obligatory, and it's just common sense. If it's moving in a spherical manner, it has to have a radius. Just the same thing. If you're going around in circles, if you're moving in circles, you have to form a radius. You have to have a radius because circles are defined by their radii. So when we look at these figures here, they are showing us a graphical, it's like a graphical definition of the movements we will be studying or the positions in a spherical manner. Then this one here now gives you the bars, and it's more of the expressions and the calculations we are going to do. So in the Cartesian plane, we had a bars E, G, K. In the cylindric coordinate system, we had E, Phi, and K, because K was axis symmetry, and it moved from Cartesian to cylindric and changed. When you come to the coordinate spheric, all of them change. Okay, in the coordinate spheric, we are going to work with ER, E theta, and this is supposed to be E phi. I know it's written EK, but it's supposed to be E phi, not EK. It's supposed to be E phi. Please note E phi. So the bars that we have in the coordinate spheric is ER, E theta, and E phi. Then we also have the radius there, telling us the distance the point is from the origin, as I explained. So if we have this point M moving in a spherical manner, it's going to have this radius telling you that, okay, M is located at this and this distance from the origin. Then we have two angles. Yesterday we had one angle in the horizontal plane because it was just moving around one axis, and that was the axis Z. So if it was going around the vertical axis Z, it was imperative, it was obvious, it was clear that it was going to only move around that in a horizontal manner. Okay, when you're going around something that's vertical, the figure you're going to form or the circle you're going to form is going to be a horizontal one. But in this case, because the symmetry is not an axis, the symmetry is a point, it forms two angles. It means it can go around that point in a horizontal manner using this angle phi that we looked at yesterday. It's going to go around like that, forming latitudes in the horizontal manner. And then it can also go around that point in a vertical manner, as in this case, the theta, it will be going like this, the vertical manner. It's going to form a vertical circle. It's like a circle that's standing straight. This one is a circle that's, we can say, lying down, inclined on the ground. So we have R telling us the distance of the point M from the origin. Then we have the two angles theta and phi. Phi is going to tell us the angle it's forming in its revolution or in its horizontal revolution around the point O or the center O. And theta is going to tell us its vertical revolution or rotation around this same point O. So in the system spheric, there's two rotations. You have the horizontal rotation, which is denoted by the angle phi, and you have the vertical rotation, which is denoted by the angle theta. That's why it moves in a spherical manner, because it rotates in the vertical sense and in the horizontal sense, forming a sphere, because a sphere is like a three-dimensional circle. So you can rotate in the vertical sense, you can rotate in the horizontal sense. It's three-dimensional, as opposed to just a mere circle. A mere circle only has one rotation. Either it's in the horizontal sense or it's in the vertical sense. For a sphere, it's three-dimensional, so we have two rotations, theta and phi. So they are telling us M est repéré par R, theta et phi. And as I told you yesterday, if they say M est repéré, it means these are what are going to help us define its position and its movements too, R, theta, and phi. So whenever we are trying to locate a point in this sphere, we are going to use these. And as I told you, R is going to tell us the distance of that point from the origin or the center, or theta is going to tell us the angle it forms in its vertical rotation, again from the origin or the center O, as I gave you the example of the longitudinal lines. And we have the angle phi, which is going to tell us its position in its horizontal rotation around the center O. Actually, theta is going to tell us the latitudinal. It's an example of latitudinal, and phi is going to be longitudinal, because it's going to be like this. It's going like that. So it's like you have longitude there, longitude there, longitude there. So if you get this point and that point, it's going to give you an angle. It's going to give you the angle between those 2 points. And this one also is going to give you the angle between those 2 points. So they're telling us here that R is equal to the magnitude of OM. So if you have from O to M, there's this distance there. Its size is R, bien sûr. Then you have theta. Theta is the angle between OZ, l'axe OZ, and OM. So you find OM is going to be making a rotation like that. It's going to be rotating like this, like this, like this, like that, OZ to OM. So if OM starts from there and it comes to this point, we know it has rotated an angle theta. Then we also have the angle phi. Angle phi is the angle between OX and OM prime. So OM prime is going to be rotating starting from X, and it's going to be going like that, like that, like that, like that, like that, and we are going to know what angle it's forming. One thing worth noting is that the angle theta is only from 0 to pi. That means it only makes a 180 degrees rotation. So it can only move from Z to down there, Z, and back. That's all, just like that. As opposed to phi. Phi moves from 0 to 2pi. So it can go from 0 to 2 pi. It makes a 360 degrees rotation. So when it starts from there, it's going to go round like that, round like that, round like that. Theta is just from there to there and back, there to there and back, there to there. It's just an angle pi. The maximum it can go is at pi, at 180 degrees. Phi goes from 0 to 360. So it can go round, it can form round, and like that, and like that, and like that. And that's that about these angles. Are there any questions so far about the coordinate spheric? Are there any questions? You guys are following, right?
Yes.
Yes.
Okay. So I take it as there's no questions. So we are going to look at the base locale, the coordinate spheric. So as I told you, the base locale is ER, E theta, and E phi. Okay, ER, E theta, and E phi. So we begin with ER. They're telling us ER est un vecteur unitaire tel que OM is equal to ROR, ER, sorry. So ER is oriented in the direction of the radius formed by that point M. So if I have my point M located there in space, the radius is going to be this one, R, and ER is going to be in that direction of that radius R. So OM is going to be equal to R suivant ER. So R is oriented in this direction of the radius formed by the point O and the point M we are studying. The point O being the origin and the point M being le point qui nous intéresse, the point we are studying. So ER is oriented in that direction. Then we come to E theta. E theta est dans le plan méridien, plan OZM, qui correspond au plan phi égale constante, directement perpendiculaire à ER. So E theta is in this plan. You see this plan which is like this? That's the plan. So you have this circle like that, this circle like that. E theta is going to be like tangent to that circle being formed by the angle theta. So the angle theta is forming a circle like this, and E theta is going to be tangent to that circle. Okay, repeat on those angles you are from explaining. So I was saying, when we are studying a point making a spherical movement, it moves, it has 2 angles to it, okay? Because the movement is spherical, it's a 3-dimensional figure, so it rotates in the vertical plane and also in the horizontal plane. So in the vertical plane, we have the angle theta, okay? In the vertical plane, we have the angle theta telling us exactly where the point M is located from OZ. and theta is the angle between OZ and OM. And I said theta, sorry, excuse me, I said theta goes from 0 to P, okay? Theta goes from 0 to P. P is equal to 180 degrees. So theta can only go from 0 to 180 degrees and back. 0 to 180 degrees and back. That's so its movement is just like that. But phi has a maximum angle of 2 pi. It goes from 0 to 2 pi, meaning it rotates 360 degrees. It goes round like that, round like that, round like that, from 0 to pi, 0, 360, 0, 360. It goes round like that. It's like it's free to rotate round to make a full circle, okay? And phi is the angle between 0 or x and 0 m prime. So it tells us the position of the point M in the horizontal plane, and theta is going to tell us the position of M in the vertical plane. This is where I gave you the example of latitude and longitude. So imagine you have, for example, we take OX there as the prime meridian, okay? The prime meridian, GMT, Greenwich, there at London, somewhere there at 0 degrees. So this is our prime meridian. And we are going to take M prime as Lusaka. And we are told that Lusaka has a longitude of 30 degrees. Yeah, Lusaka has a longitude of 30 degrees. So what they're telling you is if a point is to move from the prime meridian to Lusaka, it's going to move 30 degrees because the longitude of Lusaka is at 30 degrees. It means the angle that point is going to move from the prime meridian to Lusaka is going to be 30 degrees. That's how the lines of longitude define the position of things or of places on the globe. So you will move from the prime meridian at 0 and you will move 30 degrees to Lusaka. So that 30 degrees there is going to be our phi. It's going to tell us exactly how much you'll be moving in the horizontal plane from the prime meridian to whatsoever point you are trying to locate. Let's say you want to go to New York from the prime meridian, maybe you move something like 270 degrees. So you begin from London there and you go around in the anti-clockwise sense and you reach New York at 270 degrees somewhere there, and that's its longitude. Latitude is in the vertical plane this time. So let's say you have your equator. We can take this point as our equator, just supposing this is going to be our equator. And I tell you, okay, Australia is located at a latitude of 50 degrees from the equator. It means from the equator there, from Congo, if you're going to go down to Australia, you'll be moving an angle of 50 degrees in the vertical sense, because lines of latitude, they are oriented in the vertical sense as they go down, up and down, they're in the vertical sense in this way. Latitude 1, latitude 2, latitude 3, so they are going like that in the vertical sense. Okay, so if you're moving from Congo, the equator there, to Australia, somewhere there, you'll be forming an angle of 50 degrees on suppose, and that's going to be our theta there. That's just to help you relate a bit to something in real life that you know of. It's the same thing for this point M that we are studying now in the laboratory or whatsoever, I don't know. It's going to be forming a certain angle from the origin axis we are taking as axis to origin, which is 0z. It's going to move like that, an angle theta, and it's going to move an angle phi in the horizontal sense, and we'll be able to locate exactly where that point is. So we also use R. R now is going to tell us the exact distance. When we locate its position on the surface of the Earth, for example, using the angles theta and phi. Now to tell us exactly where it is, we are going to use the radius, which is going to tell us the distance between the origin and that point M. Is that clear? What causes the rotation of theta to be different from the other one? Okay, it's like when you look at the nature of the rotations, it's like when you're moving from this point to this point, from that point to that point, it's just going to, you cannot go round like that because the latitudes, how can I explain this? Just give me a sec, let me try and put my words together. Okay, so as I said, theta is moving, I'm sure your question is why theta is moving 180 degrees and phi is moving 360 degrees, isn't it?
Yes.
Yeah, okay. So y theta is moving 180 degrees, and y phi is moving an angle of 360 degrees. Sorry about that. I'm at the cafe, so I'm minding my talking when people come. So theta, as we have said, is giving us the vertical rotation, okay? And from the way I see things, it's like if theta is going to move an angle of 360 degrees, the other half, or like when it makes a 180 degrees, the other half is going to be redundant because it's going to be defining the same positions. Okay, so if it moves from here to here at this point, we have this angle there. But if it goes round and comes back to the same point on the other side, it's going to be at the same position. So it's just going to be redundant to define it at 360 degrees because it's going to be defining the same positions twice. That's why we have phi going at 360 degrees, telling us that, okay, this one is on the other side. It's on the other side of the circle. So theta doesn't also have to be on the other side. If we know that theta is at 50 degrees, and then we know phi is at 270 degrees. 270 degrees is going to be on the other side. So we don't need the other one to also be on the other side because one of the angles is telling us that it is on the other side. So from the way I understand it, maybe I might be wrong, but it is because it's just going to be redundant to define it at 360 degrees. It's going to be repeating the same angles over and over again. One angle phi telling us that it is on the other side of the sphere is enough. That's the way I see it. I don't know if that's clear, David.
Kindly repeat once again.
Okay, I was saying that the reason why theta is only defined up to 180 degrees is that if it goes up to 360 degrees, the other half, because 180 is like half of 360, so the other half is going to be redundant because you'll just be repeating the same angles. So let's say I'm here at point M. M is at 50 degrees. Then if I make a rotation like that of 360 and I go up to that point, this point is still going to be 50 degrees. So it's just going to be like I'm repeating the same angles over and over again. That's why we have this angle phi going round 360. So the angle phi is the one that's going to tell us to say it's on the other side. We don't need theta to tell us also that it's on the other side because it's just going to be redundant. One of them telling us that we are on the other side of the sphere, or it's in the front or it's in the back, is enough. If we get both of them to make angles of 360, one of them will be making redundant rotations. They won't be they won't be needed. Okay, we might use them, but they won't be necessary. It won't be necessary because with just this going up to 180 degrees, we can still define the position of any point on the sphere. It's like it doesn't need to go that far. We can still define it even with it going up to 180 degrees. If it goes up to 180 degrees, it will just be making repetitions, the same angles over and over again. We can say it's like the fixed rule. Yeah, we can say it's the fixed rule. It's like the convention that they made. Yeah, we can say it in that way. Then they are telling us here that E phi est un vecteur unitaire tel que le tièdre ER et theta et E phi soit direct. Yeah, so I told you guys I was going to explain this for you direct, but instead of using coordinates spheric, I'm going to use coordinates cylindric but all of them are direct. We are going to do what we did last time. I'll ask you guys to pin my video so that I show you something I scribbled on a paper. Let me just join the lesson on my phone. Sorry, I was looking for the link.
I have a question.
Yes.
Can you hear me?
Yeah.
Hello?
Yeah, I can get it. Uh-huh. You can ask. You can ask.
The rules. Okay, network is bad. I'll ask later.
Okay. Okay. Okay, so you guys can pin my video on Charles and Kalandula. You guys can pin that. You guys have pinned it?
Yes, yes.
Yes.
Okay, so we'll begin with this question here. This question here. I'm going to ask you guys these questions to see if you've been following what we've been doing so far. What's the answer to this question? What's the produit scalaire for heureux and FE? Heureux scalaire FE. The produit scalaire. You can write it in the chat here, the answer. Quickly, quickly. There's nothing to solve there. You just look at it, you apply a few principles from their definition, and you get your produit scalaire, tout simplement. Okay, someone says 1, at least people are trying. The others. Come on, guys. Only one person has tried. Even if you're not sure, we are here to learn. The essential thing is that you try. If you try and fail, you won't forget. The produit scalaire for heureux and EFI. Okay. Someone also says 2. The others, what do you think? There's 20-something of us here. If only 2 people try, it's going to be very, very worrying.
Charles,
Uh-huh.
I don't know how I can write it, but I can just say it.
Say it.
If you say modulus of EFI times modulus of this one, I don't know if it's E what. What's the angle between them?
So what's the final answer? Because you figures everywhere there. The modulus of E, you know. The modulus of E, you know. The angle between them, you know. So you can calculate their cos. Someone says 0. Okay, good. Let's continue trying. Yeah, so as I was saying, those are all numerical figures. You can calculate them and give me a figure. But you have the idea, you use that same formula, yes.
I think 0 as well.
Okay, 0, good, nice try. Come on, guys, only 5 people. Out of how many are we? Out of 26, only 5 people. If you want to learn, you have to try. You have to try. Even if you know the answer is wrong, as long as you've tried to write something or you've tried to say something, you are on the right track. Keep your ideas to yourself, you'll never learn. Okay, so people have chosen to keep silent. Anyway, we shall advance. Thank you to the 5 that have tried. Sorry, not 5, but 4. Thank you to the 4 that have at least tried to say something or type something. So, heureux, scalaire, EFI. As our friend told us, this is going to be equal to the modulus of heureux fois the modulus of EFI times cosinus of the angle between the heureux, EFI. The formula is going to be something like this. These guys form in bars, okay? Ce sont des vecteurs unitaires. They are unit vectors. So if they are unit vectors, their moduluses are all 1 multiplied by 1. And from the bars, we know, yesterday we were studying this, the coordinate cylindric. We said the angle, when I was even trying to give the expressions, I told you the angle between heureux and EFI is equal to what? I need an answer from you guys. The angle between heureux and EFI is equal to what? Yesterday we said these guys are orthogonal. They are orthogonal to each other. That means the angle between them is what?
Is it 90 degrees?
Yes. The angle is 90 degrees. So you have that as your expression. 1 times cos 90. This is going to be equal to 1 times 1. Cos 90 is equal to what?
0.
Equal to 0. That means the produit scalaire of heureux and EFI is equal to 0. So you just look at it. Heureux and EFI, we know they are 90 degrees to each other without even doing these calculations. You know they are 90 degrees to each other. That means the produit scalaire is equal to 0. I mentioned this in our first lesson. I told you guys, whenever 2 vectors are at 90 degrees to each other, whenever they are perpendicular to each other, their produit scalaire is equal to 0. These are principles you should know by now. These are principles you are supposed to have in your heart and in your mind by now, because these are the things you'll be using as you'll be calculating. You will be wasting time. When you see something like this, there's no need to even do this, because exams in Morocco are very short. You just be having your exam for about an hour, 30 minutes with a lot of questions. So here we try to not waste time on doing certain calculations. You just know them, say this and this is going to give me this. So if 2 vectors are perpendicular to each other, their produit scalaire is equal to 0. Okay, so heureux, EFI, and K are perpendicular to each other. It means heureux scalaire EFI is equal to heureux scalaire K is equal to EFI scalaire K, and they are all equal to 0. Just as E scalaire G is equal to E scalaire K is equal to G scalaire K, because even these guys are perpendicular to each other. When you come to the coordinate spheric, ER, E theta, and EFI, they are also perpendicular to each other. All of them, they are orthogonal. So that means ER scalaire E theta scalaire EFI, or EFI scalaire E theta, is going to give you a 0. Please, let's remember that these are very, very important things. Let's note that they are perpendicular, they are parallel, they are what? These are things that are going to simplify your calculations. Okay. So now, I told you guys that I was going to explain what they mean when they say tried direct. So when they tell you they are direct, this, when they tell you c'est une base directe, what do they mean by une base directe? So when they tell you heureux, EFI, and EK, c'est une base directe, what do they mean by that? So you can write them like this: heureux, EFI, and EK. When we tell you that these guys are direct, it means that you write them like this first of all: heureux, EFI, EK, in this order, obligatory, in this order. This is for the coordinate cylindric. In this order, you write them heureux, EFI, and K. You write them like that. So that means the produit vectoriel, I repeat, the produit vectoriel between this one there and this one there is equal to this one. In this, when they are moving like this, you see they're going like that. The produit vectoriel of this one and this is going to give you this. The product vectorial of this one and this one should give you the other one. The product vectorial of this one and this one should give you the other one. This is what I have defined here. It means the product vectorial of heureux and EFI. Heureux vectorial EFI should give you EK. And EFI vectorial EK should give you heureux. And EK vectorial heureux should give you EFI. Just like that, in that order. Going around like this, like this. If you go in the opposite sense, in the anti-clockwise wise, you get negatives. So that means heureux vectorial EK is equal to minus EFI. And EK vectorial EFI is equal to minus heureux. And EFI vectorial heureux is equal to minus EK. In this sense, the clockwise sense, they are positive. In the anti-clockwise sense, you'll be getting negative answers. Don't forget this. These are the things you'll be using when we start doing exercises. When you go to your faculty and you're doing TDs, when you have your exams, these are the things you'll be doing. You'll be calculating the product vectorial of these guys here, these guys here. So you have to know. You have heureux, EFI. Okay, this one is going to give me EK. You have EFI, EK. This one is going to give me heureux. You have EK, heureux. This one is going to give me EFI. If you're going in the opposite direction, heureux, EK, it's going to give you minus EFI. EK, EFI is going to give you minus heureux. Is that clear? When they say direct, c'est une base directe, it means these principles here apply. Is that clear?
Yes, clear. Can you repeat?
Okay, I'm saying when they tell you a certain base, c'est une base directe, they tell you soit une base heureux, EFI, EK, une base directe. What they mean is when you write them like this, heureux, heureux, EFI, and EK, it means that the product vectorial of this one and this one, when you say heureux vectorial EFI should give you EK, and EFI vectorial EK should give you heureux, going in this direction like this. So product vectorial of this one and this one should give you the next one, and the product vectorial of this one and this one should give you the other one there, and the product vectorial of EK and heureux should give you EFI, the next one, in the clockwise direction. Okay, clockwise direction, or clockwise direction like that. But when you start going in the opposite direction, heureux vectorial EK is going to give you minus EFI, and EK vectorial EFI is going to give you minus heureux, and EFI vectorial heureux is going to give you minus EK. When you start going in the anti-clockwise direction, they'll give you negative answers. In the clockwise direction, they'll be giving you positive answers. Est-ce que c'est clair?
Oui, c'est clair.
So if you go into the base spheric, la base spheric is going to be like this. Theta and EFI, they are also direct, like that, like that, like that, and like that. You will define them in this manner there. Yeah, you define them in this manner there. R, E theta, E phi. ER vectoriel E theta should give you E phi. E theta vectoriel E phi should give you ER. And ER vectoriel E theta should give you E phi. And you start going in the opposite direction. ER vectoriel E phi is going to give you minus E theta. E phi vectoriel E theta is going to give you minus ER. And E theta vectoriel ER is going to give you minus E phi. Just like that. Is that clear?
Basically.
Okay, love. So that's what they mean here when they say, when they tell us E phi est un vecteur unitaire tel que les tiers ER, E theta, E phi soit direct. So they're telling us it is direct. It means what I'm explaining to you. That's why they've even given us this example here. Donc, ER scalaire, E theta égale E phi, like that. How are we able to tell that the positions are at 90 degrees? It's in the definition of the bars. We know the bars is orthonomy. I explained this, it's orthonomy. Orthonomy, it means its magnitude is 1 and it's orthogonal. Orthonomy is a mixture of orthogonal and normé. So when we say a base or when we say un vecteur normé, a vector is normé, it means its magnitude is equal to 1. And when we say two vectors are orthogonal or three vectors are orthogonal to each other, it means they are perpendicular to each other, all three of them. And that's how we knew that the angles between them are 90 degrees, because these guys we've looked at, the bases we've looked at in the Cartesian, in the cylindric, and in the spheric now, they are all orthonomy. They are all orthogonal. They are all normé. It means they are all at 90 degrees to each other. Okay. Okay, lovely. Let's feel free to ask questions so no one stays behind. I want you guys to understand these things, and I want you guys to profit from this moment. As I told you, there are certain things that won't be explained to you guys because your professors are going to suppose that you guys have already seen them before, or that you just know the stuff. It's obvious, but for us it's not so obvious because we are coming from a different system and the things seem a bit different. They are the same things, but they just seem to be different. So now we look at the vector position. Okay, the vector position. So this one is it's just about the simplest amongst the three we've looked at so far, the vector position, because we already have a vector in the direction of the point M. So we have our point OM with the distance between O and M defined by R, and we have a vector in that direction ER. So we can simply say OM is equal to R suivant ER. It's like the distance is R in the direction of ER, and the vector position here OM becomes simply RER. That's all, because we already have a vector unitaire in that direction to tell us the direction. When we're defining a vector position, we just need to know the directions. That's why we use the rho, rho plus zk. We needed the rho and the k to show us the directions. That's why in the Cartesian plane, we used xe, yg, and zk. We needed the e, the g, and the k to tell us the directions. So here we have ER already telling us the direction in which OM is oriented. So we don't need anything else because ER is already there showing us, say, hey, man, OM is in my direction, it's ER. So all we are going to need is just the distance we'll need to move now from O to M, because we already know in what direction we'll be going. It's in the direction of ER in this system, the coordinate. So the magnitude or the distance we'll be moving from the point O to the point M is just R, and the vector position, the position of the vector OM or the point OM where it's located in space is simply going to be R, E, R. And as our friend asked yesterday, we are just using R, E, R for the vector position for now. What about the rest? What about phi? What about theta? What about E theta? What about E phi? Are we not going to use them? Are they useless? We are going to use them, but we will use them to define movement, not position. We do not need them for now to define the position. As long as we know in which direction R is oriented, we do not need the angles to tell us the position. For now, we are going to use them when we will be defining the movement of the point M now, or the vector OM in space. Is that clear?
Just try to repeat what you said.
Okay. I was saying we are defining vector position. So what's the vector position? The vector position simply tells us where a point or where a vector is located in our coordinate system there. And for us to define that, we need to know the directions we should go in, okay? We need to know the directions we should go in. So we need a certain vector to show us in what direction we should go in. Then that's where I said, in the Cartesian system, we use OM equal to XE plus YG plus ZK, because there we had the E telling us, okay, move X steps in the direction of E, then move Y steps in the direction of G, then now move Z steps in the direction of K. Then we came to the coordinate cylindric. We said OM égale à rho, E rho plus ZK. So there we had E rho and K telling us in which directions we should go to find the position of that vector OM. So we had rho telling us, hey, move rho steps in my direction, and then K is telling us, oh, and then move Z steps in my direction. So even in this system, we are going to need to know which direction we should take to locate this vector of M, or to find le point M in our coordinate system there. But for this one, it's simpler, it's simplified, because we already have a vector oriented in the direction of OM. In the Cartesian plane and in the cylindrical plane, we had to take some long cuts. We couldn't go directly from O to M. We had to go from O to M, prime them to M, or we had to go from O to X, then X to Y, then Y to M. It was a bit more complicated because there was no vector in that coordinate system to take us directly from the origin O to the point M. But alhamdulillah, in the spherical system, we have the vector ER oriented directly in the direction of OM. So that's all we are going to need. So when someone asks us, where's the point M located in space, we just tell the person, move our steps in the direction of ER, because ER is oriented directly in the direction of the radius or the point OM, and the vector position becomes RER. That's all we need for now to tell us the position of a point in the spherical coordinate system. We just need the radius and the direction of the radius, and we find our point there using this distance between O and M and the direction ER simply. Is it clear?
Yes, it is clear.
Okay, lovely. So now we are going to do what we did yesterday. We are going to try to transition from spheric to Cartesian and vice versa, so that we know when we are moving from the spheric coordinate system to the Cartesian coordinate system, what expressions we are going to be using. And as I have told you, I know these expressions like R and theta, they seem very long. I mean, sine theta, cos phi, sine theta, sine phi, cos theta, they look complicated, but it's very simple. It's just the exact same things we were doing yesterday. It's just that this time we need to extract two triangles and two projections. So what we are going to begin with first is find the expressions for x, y, and z, these guys from the Cartesian plane, in terms of r, theta, and phi, these guys from the spheric coordinate system, because we are moving from there to there. So we need to find expressions for these in terms of these. And like yesterday, I tried to reproduce this figure here. I drew it there. This figure here is the figure we are going to be using. This one here, I have reproduced it down here, and we are going to try to extract triangles and work with them. As I told you, always work with right-angled triangles. Bon, c'est parti. So we have this point there, we have this point there, and we have this point there. Okay, we have this M prime, and we have that, like that, the way it is, R, theta, and E phi. So we will begin first by extracting our first triangle. The first triangle we are going to extract is going to be in the vertical plane, because when you want the expressions for x, y, and z, we are going to begin from the vertical plane first. We find the expression for this line here. We cannot begin from down here because we do not know what this line is equal to. In the coordinate cylindric, we knew it was rho, but rho is no longer applicable here. We do not have rho in the coordinate spheric. So, pour le moment, for now, we do not know what this 0 m prime or O m prime is equal to this line. So we need to find its value. So how are we going to find its value? We are going to begin from up here. From up here, we get its value. Then we'll come down here with its value and find the expressions for x and y when we do some projections. So I know that the vertical plane is perpendicular to the horizontal plane. Okay, z is perpendicular to x and y because they are orthogonal. We already looked at this. And if z is perpendicular to these two, it means it is perpendicular to this line also, OM prime. Okay, it's perpendicular to it. For now, I'll call it a rho, but we are not going to use it as a rho in our coordinate system, this time the spheric coordinate system, but we can just denote it as rho so that it simplifies our calculations. So z is perpendicular to rho because rho belongs to the same plane as x and y, and z is perpendicular to that plane. So we have z and rho being perpendicular to each other. So we can use that as our right angle triangle because they are perpendicular to each other. So what I'm going to do is I'm going to get this rho and I'm going to project it upwards perpendicular. When I project it upwards, it's going to come here from Z to M, okay? Because from M to M prime, it's just a straight line there. So if I have this and that, and I have this in the middle, I can project this up here, and I'll have something like this up here, and I'll have this right angle triangle there, because the angle between rho, which has come up here, and Z is going to be 90 degrees. So I'll have Z, R, and rho, Z, R, and rho, with a 90 degrees between rho and Z, and an angle theta between R and Z. So I extract my first triangle. It's a vertical triangle. I have my Z, I have my rho at 90 degrees, then I have my R there, R meeting Z at theta, this angle theta here, this one here. Is that clear how I have gotten this triangle there?
This is clear.
Yes.
I've got a question.
Yes, yes.
You said that Z is both perpendicular to Y and M.
X.
Hello?
Yeah. Continue. I can get you.
I'm saying that you said that Z is both perpendicular to Y and M prime, and including X.
Yes, it's perpendicular to all of them.
But how come? How possible is it that it can be both perpendicular to Y and M prime at the same time?
Let me demonstrate. Sure. I'm trying to. Let me just try to. Sorry. Just give me a sec. Just a minute. Okay. Okay, you guys can pin my video again. You have pinned it?
Yeah.
Okay. You can see the way these guys are oriented with each other. This is my X, this blue pen. The black pen is my Y, and the Z is like this. So you have seen these guys are horizontal. They are facing down like this. And I have my Z in the vertical plane. It's going up like that. You guys can see that, yeah?
Yes.
Yeah, so this is perpendicular to that. It's 90 degrees. The angle between these two, the X and Y, is 90 degrees. And this Y is perpendicular to this horizontal plane. It's perpendicular to it, the Y. Oh, the Z, sorry, the Z, the ruler, is perpendicular to both these two because they belong to the same plane. Here, I have a 90 degrees like that, and from this side, I have a 90 degrees like that. So the Y is, the Z is perpendicular to the X, and the Z is perpendicular to the Y at the same time because they are oriented like that. Then between the X and the Y, I have this OM prime, the pencil that I've put in the middle. That's how the figure is. In the middle, I have this OM prime or rho. Do you see that the Z is still perpendicular to this one? Because these are all in the horizontal plane, and the vertical plane is perpendicular to the horizontal plane. So anything I'll include, even if I include another figure, sorry, I've run out of pens. Okay, we'll use this water. I include this water in the horizontal plane. The Z, the Z, which is in the vertical plane, will still be perpendicular to this water here in the horizontal plane, because the vertical plane is always, it's going to be perpendicular to the horizontal plane. So this is OM prime. Picture this as OM prime and picture this as your Z. You see they are perpendicular to each other. And that's why I'm going to use them in my triangle. Okay. Then I have my arrow. My arrow is oriented in this direction like this. So it's going to be appearing as something like this. I have my OM prime, then I have my Z, and I have my arrow there like that. The Z and the O, they are perpendicular to each other. I don't know if it's Olivia, you have your hand up. Okay, it's glitching. Yeah, I have seen from my PC also it's glitching. But have you guys gotten what I have said, or should I repeat?
Repeat.
Okay, so I gave you this as our plane, okay? Our XOYZ plane. It's like that. So this is my X, this is my Y, and this is my Z. So notice the way the X and the Y are oriented, or the way they are. They are facing, like they are lying down, so to say. They are lying down. They are in the horizontal plane. So it's clear about the X and the Y being in the horizontal plane.
Yes.
So X and the Y are in the horizontal plane like that. Then the Z is in the vertical plane. Notice it's facing up. These two are oriented like this, or in the horizontal plane. The Z is standing straight, okay? It's in the vertical plane. It's vertical. These are horizontal, horizontal. This one is vertical, okay? So we know these three from their definition, they are orthogonal. They meet at 90 degrees to each other. Now, how's that? How's that possible? So the x and the y, we put them at 90 degrees to each other like this. We make sure the angle between them here, this angle between them is 90 degrees. See, the angle between the x and the y is 90 degrees. Then they form the horizontal plane, the two of them. And because they are in the horizontal plane and the y is in the vertical plane, the y is, sorry, the z, this is z, the ruler, the z is going to be perpendicular to this horizontal plane, this whole plane here formed by these two. The z is perpendicular to it. It's just common sense. When you are standing on the ground, you are perpendicular to the ground because you are standing vertically and the ground is lying horizontally. So the vertical plane is mostly at 90 degrees to the horizontal plane, unless there's an inclination. But here there's no inclination. The z is straight up, straight up. Whenever you stand straight, when you stand straight, you are vertical also. Yes, you are in the vertical plane. Oh, come on. Sorry about that. You guys can hear me, huh?
Yeah.
Okay. Sorry, like the Wi-Fi can't support two devices. I'm using my phone and my PC, so died out. Let me switch to mobile data on my phone, and we can continue my explanation. Okay, so I was telling you guys that whenever you are standing straight, whenever you stand straight, no inclination, no whatsoever. When you stand straight, you are at 90 degrees to the ground. Okay, so even this z-axis there, the vertical axis, it's standing straight. And since it's standing straight, it becomes perpendicular to the horizontal plane, which is lying on the ground, so to say, or facing the ground. It becomes perpendicular to it. So the 90 degrees is perpendicular to this plane. That means the z is going to be perpendicular to the y. If you just come like this, the horizontal plane, and the z is again going to be perpendicular to the y. So it's perpendicular to both the x and the y, because these two are in the horizontal plane, perpendicular to each other, and the y is in the vertical plane. And the vertical plane, whenever the vertical plane is standing straight, it's going to be obligatory. It's going to be perpendicular to the horizontal plane. So knowing that x, y, and z are all perpendicular to each other, if I introducing my rho or the OM prime, I'm going to put it in the middle of y and x as in the figure we have, like that. Okay, so this is my x, this is my y, and this is my OM prime. It's the way it is in the figure, not so. The OM prime is between x and y, and this is my angle phi. Yeah. So because y is perpendicular to the horizontal plane, it's still going to be perpendicular to this OM prime, because OM prime belongs in the horizontal plane, and the y is standing, the z is standing straight to the horizontal plane. This OM prime, this rho, I have introduced it in the horizontal plane. It's in the horizontal plane. So whatsoever is standing straight here in the vertical plane is going to be perpendicular to it. Okay, like that. X, y, and rho are in the horizontal plane. That means z, which is in the vertical plane, is perpendicular to any line you can draw in the horizontal plane. The z will be perpendicular to it. That's when I introduced in this bottle of water. If I introduce this bottle of water also in the horizontal plane, the z, which is in the vertical plane, will still be perpendicular to this water bottle, which has joined the horizontal plane. Is that clear?
It's clear.
And for everyone else, it's clear.
Clear.
Yes, it's very clear.
Okay, awesome. So we go back to our lesson. C'est quoi ça? Share screen. Oui, partager. Just stop video aside. Okay, so that is why here I was able to extract, where am I? Not on this page. Yeah, so this is what I was showing you now. The Z vertical to the horizontal plane, the X, the Y, the blue pen, the black pen, and the pencil. The ruler here, the Z, is perpendicular to all these guys. So if I just get this part now, I just get this part, which is interesting me, the Z, the ruler, and the pencil. They are at 90 degrees to each other. Then I have this R between them, okay? So I can simply just project this OM prime or the rho, I can project it upwards. Here, I can draw it there. Parallel, as I told you, parallel vectors are the same. So I can project this there and have something like this. If not, I can project the Z this side, okay? In this figure, I projected the Z. The Z, I can bring it here, and I'll have this figure like this. And because Z is parallel to OM prime, when I project it this side, it's going to be perpendicular. Sorry, not parallel, but perpendicular to OM prime. When I project the Z this side, it's going to be perpendicular to this OM prime here. So I can get this triangle there, this triangle like this. I've gotten this triangle, which is this triangle I have formed here, the rho, the Z, and the R with theta there, okay? So you guys have gotten where this has come from, this triangle here.
Yes.
And this theta, the angle, I know the angle theta is here. When you use N property, you guys remember angles, N property, the N, Z here is forming Z, R, Z. It's forming an N. So which means the angle here is equal to the angle there. That's how come I have this theta up here. Then from here, after extracting this triangle, I can simply use Sohcahtoa to find the expression for Z and rho. They are the ones I'm looking for. I want the expression for Z and for rho in terms of R, theta, and phi. Okay, so we begin with sinus. We say sine theta. Sine theta is going to be the opposite over the hypotenuse. The opposite is rho, and the hypotenuse is R. So it's going to be rho over R. And we have our rho, or our OM prime, being equal to R sine theta. So if you are writing this down, you can just write this line, OM prime is equal to R sine theta, because we are coming to use it. And then the Z, because we need the expression for Z also. We are moving from Cartesian to spheric. So we need the expressions for X, Y, and Z in terms of R, theta, and phi. So how are we going to write Z in terms of R, theta, and phi? We can simply use this figure here by simply saying cos theta is equal to the adjacent side Z over the hypotenuse side R, and Z is going to be R cos theta. That's why when you come here, Z is equal to R cos theta. That's where it's coming from the vertical triangle we have extracted here. So this one we keep it as Z, R cos theta, simply Z. Then from here now, we need to find the expression for X and Y, okay? The expression for X and Y. So we need to extract another triangle that we are going to use to find the expressions for X and Y. Yeah, X and Y. So we are going to use the same triangle we used yesterday. If you guys, that's why I told you, if you revised what we did yesterday, today's work should be relatively simple for you. We are going to use this figure here. This is the figure we had yesterday when we were doing the coordinate cylindric. So we are just going to get this Y and project it this side. We project this Y there. When we project this Y there, like we did yesterday, the angle between X and Y is 90 degrees. So when I bring this Y this side, I'll have a 90 degrees there, and I'll have my right angle triangle as that there. So my right angle triangle will be X, Y, and OM prime, or rho. But I have the expression for rho in terms of R and theta, which I'm working with in this time, this time. So this one here is R sine theta. I'm very sorry, I forgot to write sine theta here. I made a mistake. I wrote cos theta, so I put blanco there, and I was supposed to write sine theta, but I forgot. So this one here is supposed to be R sine theta, because this line here, the hypotenuse is this line here that we are from solving rho. rho, this line here, the rho we got here, it's r sine theta. So this is r sine theta, and we have our x and we have our y meeting at 90 degrees. So what we need to do now is just to use Sohcahtoa. So we begin with cosinus this time. We'll say cos phi. Cos phi is going to be equal to the adjacent side x over the hypotenuse r sine theta. The hypotenuse is r sine theta. So it's going to be x r sine theta, and x is going to be equal to r sine theta times phi. So we'll have x being equal to r sine theta cos phi, which is what they have here. X is equal to r sine theta cos phi. Then when you come this side, we now use sine. Sine of phi is going to be equal to the opposite side, which is y, over the hypotenuse side, which is r sine theta. So we will have our y being equal to sine theta, or r sine theta multiplied by sinus of phi, which is what they have here. Again, y is equal to r sine theta sinus of phi. Which is what they have here, r sine theta sine phi. So we have our expressions for x, y, and z in terms of r, theta, and phi. Cartesian to spheric, we have x being equal to r sine theta cos phi, y being equal to r sine theta sine phi, and we have z being equal to r cos theta. Then, like I did yesterday when I was trying to show you, we are now going to try and find this one here, this one. We are going to try and find this one there. Using the same things I told you yesterday when we were trying to calculate the expression for and phi. Okay. So for c'est un vecteur unitaire. Okay, and so is a unit vector, and we know that the magnitude of the vector, this vector here in the direction of is equal to r. Okay, so if we're just dealing with this time around, it means r is equal to 1. Just like yesterday when we were calculating rho was equal to 1, the magnitude, because rho is a unit vector. is also a unit vector. That means its magnitude, which is r, is going to be equal to 1. So when r is equal to 1, we just get these expressions here like we did yesterday. So when r is equal to 1, x will be equal to sine theta cos phi without the r, because the r is 1, and y is going to be equal to sine theta sine phi, and z is just going to be equal to cosinus of phi. Now, since we are moving in the Cartesian plane, we need to express it in terms of x, y, and z. It's like in the Cartesian plane. So from O to M in the Cartesian plane, we'll move x, y, and then z. X, y, and then z. So for us to move from 0 to r on this line, we'll move x, y, and then go up z, and we reach r. X, y, and then z, like we did in the Cartesian plane. And we have our expressions for x, we have our expressions for y, and we have our expressions for z. Taking into consideration that r is equal to 1 because we are dealing with a unit vector, r, and when r equal to 1 is going to be equal to sinus, is going to be x suivant i plus y suivant j plus z suivant k. Like in the Cartesian plane, the things we look at in the Cartesian plane, x suivant i, y suivant j, and z suivant k. And we have our expressions for x, y, and z in terms of the coordinates in the spheric system. So x is equal to sine theta cos phi. It's going to be equal to sine theta cos phi suivant e. The x is always following e. Then the y, which is following g, is going to be sine theta sine phi. So it's sine theta sine phi suivant g. And the z, which is r cos theta, but because the r is equal to 1, will be cos theta, and because z follows k, it's going to be cos theta k. Is that clear? Okay.
A question.
Yes.
On the second triangle, where thinking X and Y.
Uh-huh.
How
Where X and Y are meeting, you come here. You come here. Can you just mute your mic? There's a sound in the background. That's okay, good. So X and Y are orthogonal to each other. They are meeting at 90 degrees. So we are going to use these two to form our right angled triangle. So either we project the X and bring it this side, but I did not because I knew it was going to interfere with this line. It's not going to be clear. So we can bring the Y. We can get the Y and project it this side so that we form a triangle. So when I get this Y, I bring it this side, it will come from here and go all the way up to there. And I'll have my right angle triangle, which is this X, Y, and R sine theta or the rho. Okay, and X and Y are meeting at 90 degrees. So they will be at 90 degrees to each other here because I have projected this Y down here. Is it clear?
it's clear.
So what we're going to do now is the next up we're going to calculate is E theta. But I'm not going to do this one. I'm going to give it to you guys as homework. But the homework, you don't send it to me. You have the answer here already. I just want you guys to try and derive this formula. Yesterday when I calculated E, I then found E phi. So go and look at what I did after I found E for me to find E phi. Look at that and then try to use that to calculate F theta. Just make sure you get this expression out of it. It's going to be your work to try. That's for you to try and understand extracting triangles and all. Okay, is it clear?
It's clear.
Okay, and then also you are going to try and find these things. Maybe next week I might go through them with you guys, but I just want you guys to try. It's the same things we did with the coordinate cylindric yesterday. Try to use those things we did to get these things, okay? Remember, arctan is simply tan inverse, arccos is simply cos inverse. So try to find those, try to get these expressions. Just start from here, add, subtract, multiply, whatever you have to do, divide, use these and get these like I did yesterday. Remember, for us to get here, we added this, and then for us to get phi, we divided these. So it's going to be the same thing. As you can see, there's addition there. So for you to get this expression, you have to add something there. And for you to get this expression, there's division. You need to divide some things there. And for you to get this again, there's division somewhere here. So you need to divide some things there, simplify, multiply by something, and get your answers. So I just want you guys to try. It's just so that you can learn how to do these things, just to see if you have understood. And in trying these things, you see what you've gotten, what you haven't gotten. And I recommend you work in groups. Don't try and work alone. You might have gotten one part, your friend might have gotten another, and there's a part that you didn't get that your friend got. So try and work with your housemates, your roommates, whatever. Just work out the rest of the work here. This and these two, find them. They will be very simple. Just use what we did in the coordinate cylindric and what we've done today also, and try and get these expressions. Okay?
Yeah.
Good. Make sure you do it. I recommend that you do it. It's going to really help you learn. If you want to learn how to do these things, do it. For me, I won't check who's done it. As I have said, don't send me the answers. Just compare with the answers you have there. So I won't check who's done it. It's just up to you yourself to realize just how important it is for you to do it. And then you do it. Okay?
Okay.
Awesome, guys. Now we come dériver d'un vecteur unitaire par rapport à un angle. Okay.
Before we move,
Can we, I'm asking, can you show me the E theta, the direction of E theta?
If is when you get your direction of ER and E theta, if is just going to be perpendicular to them, okay? It cannot be properly represented there, but it should just be in a way that it is perpendicular to both ER and E theta. This is where your imagination is called into play. Just imagine E phi being perpendicular to both ER and E theta, okay?
That means it's going in the direction like Z.
In the PC, no, it's going in the PC.
Which direction?
Like the direction going, you've seen ER and E theta is like they are oriented, they are horizontal to the surface of the screen. You see in my PC, the screen. I have drawn ER and E theta on their surface. Huh? That means EK should be coming out of the PC. Can you imagine that?
Oh, yeah.
Yeah, it should be coming out of the PC. That's the only way it's going perpendicular to them. Okay, not the only way, but it's going perpendicular like that.
Okay.
Yeah. I hope you've gotten what I've explained. Huh?
Yes, yes.
All right, awesome. Any other questions before we do the derivative? Okay, no questions. Silence means no questions. Awesome. This is a very simple part. It's a tool we are going to use as we will begin to do the velocities and the accelerations. So understand it well. It's very simple. It can be proven, but after we prove it, there'll be no need to go back to it every single time. You just have to know it by heart, in your mind, in your soul, with your everything that it is this, and continue using it until you get your 18s and 19s in mécanique du poids. So, on sait que E est un vecteur unitaire de module constante. Then on derive E par rapport à phi. So we are deriving E par rapport à phi, like that. This is just notation. Don't worry. When we're deriving it, as I told you, the derivation is like rates of change. So it's like we have E moving about with phi changing. Okay. Let me come to the figure. Where's that figure? The figure is down here. So imagine this is heure. Heure is moving like this. As I told you, it moves like that. And as it is moving, phi is changing. So what we want to calculate is the rate of change of heure with respect to phi. How is phi changing as heure moves? That's what we are trying to calculate here. Derivative is simply rates of change. So we have that here. This is just notation. Then we have exprimons heure en fonction de la base cartésien. So the derivative of heure par rapport à défi is a certain other unit vector. So we are trying to show what that is by using this. Okay, so we have heure equal to cosinus phi e plus sinus phi g. Now we are going to derive this expression par rapport à phi. So we have d de heure par rapport à défi is going to be equal to the base IJK. This you have to remember. You have to remember. IJK, c'est une base fixe. Okay? It's constant. C'est une base fixe. It doesn't change. So when you're deriving E, when you're deriving G, when you're deriving K, it's always equal to 0 because IJK is a fixed base. Remember that EJK is a fixed base. The others like heure, phi, theta, r, those are mobile. They move, they change. But EJK from the coordinate Cartesian is fixed. It's constant. It doesn't change. So its derivative is equal to 0. So when we will be deriving here, E is a constant. We'll just leave it out. We won't derive it. We'll only derive cos phi. G is a constant. We won't derive it. We'll only derive sinus of phi, and the derivative of cos phi is equal to minus sine phi. I'm sure you know this. And the derivative of sinus of phi is going to be equal to plus cos phi. If you don't know the derivative of cos, sine, tan, and all that, learn that today. Today, it's obligatory that you learn that today. That's what we'll be using in mechanics. So if you cannot derive cos and sine, learn how to do that. I told you guys learn calculus, I told you learn trigonometry, because that's all we'll be using. Okay, not all, but that's what we'll be using for the most part. So when you derive this expression, the derivative of cos phi will give us minus sine phi, par rapport à phi, of course, and the derivative of sine phi is going to give us plus cos phi, par rapport à phi, bien sûr. So when we derive this expression, when we derive heure par rapport à phi, it's going to give us this. Now, what's this equal to? Minus sine phi plus cos phi. What's it equal to? Minus sine phi plus cos phi. When you come up here, from the coordinate cylindric, when you come up here, you realize that E phi is equal to minus sine phi e plus cos phi g. Wow, notice that? We derived E and we got minus sine phi e plus cos phi g, which is E phi. That tells you that the derivative of E par rapport à l'angle phi is going to give you E phi. So when you derive E par rapport à phi, it should give you E phi. And that's what they were trying to show you here. The derivative d'un vecteur unitaire. So d de de phi is going to give you E phi. And that's what's highlighted here. D de par rapport à de phi is going to give you E phi. It's just, there's nothing special, there's no magic there. It's just calculus and trigonometry. You just derive the expression for that we got yesterday. We proved this. When you derive this, it's going to give you the expression for E phi, and that's what you are going to use. And here we get a rule. Okay, we get a rule. But before we get the rule, we are going to try and derive E phi also. When we derive E phi, you have minus sine phi plus cos phi. The derivative of sine phi is cos phi. So you have minus cos phi suivant I plus derivative of cos phi is minus sine phi. So you have minus cos phi minus sine phi g. Your answer there, minus cos phi e minus sine phi g. And this is simply equal to negative of E. You just multiply this expression by minus. It's going to give you minus cos phi e minus sine phi g, which is equal to minus E rho. And from here, we get the general rule. On remarque que la dérivation par rapport à phi correspond à une rotation de pi sur 2. Remember I told you, and I emphasized this when I gave you that question, E phi, and K are at 90 degrees to each other. But here we are just dealing with E and E phi. They are at 90 degrees to each other. So when you derive E, or when you derive a unit vector, in this case E and E phi, par rapport à l'angle phi, it's like you've rotated 90 degrees. So from when I derive par rapport à phi, it's like I have moved 90 degrees. And when I move 90 degrees, I'm going to find myself at phi. And then when I derive phi again, par rapport à l'angle phi, it's like I am rotating 90 degrees. So I'll rotate 90 degrees this side, and I'll find myself in the opposite direction, which is going to be minus And when I derive minus if you want to try deriving minus you will rotate 90 degrees and you'll find yourself in this direction here, which is in the opposite direction of phi, and you'll find that you have minus phi. So another homework, try to prove this. Try to see if the derivative of minus is going to give us minus phi. Okay, try deriving it. It's simple. It's just a derivative of cos phi and the derivative of sine phi. See if it's going to give you minus phi. And just like that, whenever you derive this unit vector par rapport à phi, it's like you have moved 90 degrees. And when you move 90 degrees, you find yourself at phi, because and phi are at 90 degrees to each other. They are orthogonal. Emphasis, they are orthogonal. That means they are at 90 degrees to each other. So when you derive it's like you've rotated 90 degrees. So when you rotate 90 degrees, you will find yourself at phi. So the derivative of de phi is going to give you phi. Then when you derive phi par rapport à phi, it's going to give you minus And when you derive minus par rapport à phi, it's going to give you minus And when you derive minus sorry, not minus but minus phi. And when you derive minus phi par rapport à l'angle phi, it's going to give you And just like that, just like that, just like that. So if you perhaps you won't remember this at the beginning, you can still draw this when you're working out your questions. You can have phi minus and minus phi. Even I used to draw it so I don't make any mistakes. So you just know when I'm deriving phi par rapport à phi, I know I'm moving 90 degrees, so it's going to be phi. When I'm deriving phi par rapport à I'm moving 90 degrees, so it's going to be minus And when I'm deriving minus par rapport à phi, I'm moving 90 degrees, so it's going to be minus phi. Is that clear?
clear.
Okay. Okay, so it's clear? No, not clear. Okay, so I was saying, we are trying to calculate the derivative of heureux par rapport à phi. De heureux par rapport à phi. So the expression for heureux is this one. We calculated this yesterday. It's equal to cos phi e plus sinus phi g. So here we have a product. We have cos phi and e. We have sin phi and g. So normally you'll be forced to use the product rule when calculating the derivative. Sorry, give me a sec. Okay. No, it's all right. We can continue. You have to use the product rule, but we will not use it this time because E, G, K, if K was included, they are fixed. I told you E, G, K, c'est une base fixed. It's constant. It does rate of change. So if there's no change, if something is fixed, its derivative is equal to 0. So here we'll not be deriving E and G, we'll just be deriving cos and sine. For clock for integration, I'm not sure. I have never tried to do it before, but I think it can be the case if you yeah, it's correct, because if you go clockwise, you'll be integrating it, but we do not work so much with integration, so I never really paid attention to it before. But thank you for the remark. Integration is going to be in the clockwise direction. C'est très bien ça. So yeah, when you derive cos phi and sin phi, the derivative of cos phi is minus sin phi. That's par rapport à phi. Huh? The derivative of cos phi par rapport à phi is going to give you minus sin phi. And the derivative of sin phi par rapport à phi is going to give you cos phi. So when we derive heureux par rapport à phi, we are going to have minus sin phi e plus cos phi g. Now, when you look at this expression, minus sin phi e plus cos phi g, it's equal to E phi. That's what we found yesterday when we calculated E phi. It was equal to minus sin phi e plus cos phi g. And that tells you that the derivative of heureux par rapport à phi is going to give you E phi. Okay, d de heureux par rapport à phi, ou bien d de heureux de phi is going to give you E phi. In the same manner, when we try to derive E phi now, when we try to derive E phi is equal to minus sin phi e plus cos phi g. So I derive sin phi. Sin phi is going to give me cos phi. So I'll have minus cos phi. When I derive cos phi this side, it's going to give me minus sin phi. So my final expression is going to be minus cos phi e minus sin phi g. And you'll notice that this is just equal to minus E rho. Okay, it's just equal to minus E rho, because E rho is equal to cos phi e plus sin phi g. And if I multiply this by minus, it's going to be minus cos phi e minus sin phi g, which is this one here. So the derivative of E phi is equal to minus E rho. That's where now we can make a remark, we can establish a rule, which is that when you derive la dérivation par rapport à phi correspond à une rotation de pi sur 2. So when I get heureux and I derive it par rapport à phi, it's like I am rotating 90 degrees. And as we have emphasized several times, I don't know how many times I have said this, heureux and phi are orthogonal to each other. They are at 90 degrees to each other. So if I rotate heureux 90 degrees, I'll be rotating it into phi. That means heureux is going to become phi. So if the derivative of heureux par rapport à phi is a rotation of 90 degrees, it means the derivative of heureux par rapport à phi is going to be equal to phi, as we have seen from the calculations we did above. When we derived heureux par rapport à phi, it gave us phi. That implies the derivative of heureux par rapport à phi is a rotation of 90 degrees, which is going into phi. De même, when you derive phi par rapport à phi, you will rotate 90 degrees. And when you rotate 90 degrees, you'll be going in the opposite direction. It's like you have rotated 90 here and 90 there. So you have rotated 180 degrees. So you have gone in the direction or in the opposite direction of heureux. And if it's in the opposite direction of heureux, it means it's moins heureux. That means the derivative of e phi par rapport à phi is going to be moins heureux. The same thing, when you derive that moins heureux par rapport à phi, you rotate 90 degrees again. You rotate 90 degrees. When you rotate 90 degrees, you will reach here. And when you reach here, you'll be on this vector here. And this vector is in the opposite direction of e phi. It means it's moins e phi. That's why I told you, try to derive moins heureux and see if it's going to give you the expression moins e phi. Then you will know that this is accurate, and it's accurate because it's going to give you moins e phi. If it doesn't give you moins e phi, it means you have made a mistake somewhere in your derivative. So that's that. When you derive these heureux e phi par rapport à phi, it's like you are rotating them 90 degrees. And since they are at 90 degrees to each other, it's like you rotate them into each other. It's like you move heureux and you move it into e phi. So it's going to become e phi. And when you derive e phi again by par rapport à phi, it's like you have rotated it 90 degrees. So it's going to become minus heureux because these two are at 90 degrees to each other. Is that clear?
It's clear.
Okay, good. So we have finished this last part of this PDF. I really wanted us to begin the vector vitesse today. So next week we just finish up with the vector vitesse and the accelerations and all. So straight away, in the last 10 minutes we can begin that. What's up with this? Okay, very much clear. Awesome. So vector vitesse. You guys know what vitesse is, not so? Velocity. What's velocity?
The rate of change of distance with respect to time.
Yeah, the rate of change of distance or displacement rather. Because distance is a scalar, so we use displacement, which is a vector.
Oh yeah.
Because velocity is a vector. But that's good. As long as you get the concept, it's the rate of change of displacement. So even here, that's what we'll be calculating. As I told you, we are studying movements. In cinematics, we are studying movements. So it's like our vector OM or our point OM is moving in space now, and we're trying to calculate its velocity, how much it's changing with respect to time. Then we are also going to calculate the acceleration, how much the velocity is changing with respect to time, then cinematics. So what they are showing you here, they're telling you soit un référentiel donné R O X Y Z, considérons un point matériel en mouvement. Il se trouve en M à l'instant T. So here, à l'instant T, we imagine T maybe 0 seconds, it's at M. Et on M prime à l'instant T plus delta T. So let's say it moves for 5 seconds. So now we have, it is going to be at M prime at 5 seconds. So this is just going to be 0 plus delta T, which is 5. So it's going to be M prime at 5 seconds. So it has moved this distance, M prime, M in 5 seconds. So now you are to calculate the speed or the velocity. I remember we used to calculate the speed is equal to distance over time. So you just get the distance, it's moved, divided by its time. You get the displacement, it's moved, divided by its time, and you get your velocity. Or you can just get the distance and derive it with respect to time. If the distance has been expressed in terms of time, you can calculate the velocity from deriving it. So we know V here, la vitesse, it's a vector, so you should always put a flash on top of it. Always vector vitesse of M par rapport à R is going to be equal to OM prime, the distance. Here we're getting the distance OM prime minus OM for us to get the distance between the 2 points divided by the time, as I told you, delta T. Just the same formula you are using, distance over time. And you get that. So it's going to be delta OM over delta T. The change in distance over the change in time. Yeah, the distance moved over the time of the displacement moved over the time of same thing, same physics you are used to in high school and wherever you did velocity, acceleration et tout ça. La vitesse de m, vitesse instantanée, est, so we have this vitesse being equal to, so when we calculate la limite lorsque delta t tend vers 0, this, from calculus, you know that when we have delta OM divisé par delta t, lorsque delta t tend vers 0, it becomes its dérivée. So it becomes la dérivée de OM par rapport à t, de OM sur dt. This is just calculus. As I've told you guys, please do it if you haven't done it. And finally, we get our expression there. When we want to calculate the vitesse of a vector, we will just derive its vector position. That's why we were calculating the vector position, or we were finding the expressions for the vector position when we did the system de coordonnées. We are just going to derive that vector position par rapport au temps, and we get the vitesse. Simply, it's very simple. You get your vector position, you derive it, and you get your velocity. Tout simplement. So now, we will go coordonnée par coordonnée. So we have a composant de la vecteur, composant de la vitesse en coordonnées cartésien. Okay, so here is going to be a new notation. It's nothing to be freaked out about. It's just simple. So we begin with our vector position, OM. Vector position OM equal to xi plus yj plus zk. So the vector vitesse here is going to be the derivative of this, de OM par rapport à t. De OM par rapport à t. So I told you guys that EJK is fixed. Remember? Yeah, sure you remember. I told you it's fixed. So its derivative is equal to 0. That's why here they have, in this highlighted part here, they have told you d de I par rapport à t, d de G, d t, d de K, de t, they are all equal to 0 because EJK are all fixed. C'est une base fixe, EJK. So we just derive x, y, and z. Now, this x, what's x? X can be anything on the x-axis. Okay, it can be 5, it can be 6, it can be 2.1, depending on whatever unit of measure you are using. X can be anything. X there is just telling you that, okay, you are on the x-axis, so it can be any number on the x-axis. Same thing to y. Y can be any number on the y-axis, and they change because these vectors are moving. So it's like their positions on the axis are also changing. So we just denote them with x, y, and z to show us that, okay, here we are on the x-axis, there we are on the y-axis, and there we are on the z-axis. Okay, so when we derive them, d de x par rapport à t, d de x dt, you're just going to write x with a dot on top. Because x can be anything, we don't know what it is. So we are just going to write x with a dot on top to show that we have derived the x is the derivative. That's why here we have x with a dot on top here. I don't know if it's clear, but there's a dot on top. We read it as x point. La dérivée de x par rapport au temps, c'est x point. Simple, just x point. Dérivée de y par rapport au temps is going to be y point. Y point. Just write the dot on top. And the derivative of z par rapport au temps is going to be z point. This is just to show you that we have derived. Okay, this is just to show you that we have derived these x, y, and z. It's no longer x, it's now the derivative of x. So you say x point, y point, z point. So the vitesse in the coordonate cartésien is going to be x point suivant i, y point suivant j, plus z point suivant k. Simple as that. X point. Okay, I had network issues, so I didn't get anything. Okay, I was saying, for you to calculate the vitesse, you're just going to derive OM, the vector position, because this is what's showing us the distance, okay? Vitesse is going to be is equal to, or velocity is equal to the derivative of the displacement with respect to time. So here we're just going to derive OM, and we know OM in the coordinate Cartesian is equal to XE plus YG plus ZK. So we are just going to derive this. And I told you guys before that EJK are fixed. Okay, it's a fixed bars. They do not change, they are constant. So their derivative is equal to 0. So here we are just going to focus on the X, the Y, and the Z. So we are going to derive X par rapport au temps. We're going to derive Y par rapport au temps. we are going to derive z par rapport au temps. And I said the x it's just telling us that you are on the x-axis. The x can be anything on the x-axis. It can be 5, it can be 6, it can be 100, it can be infinity, it can be what? All it's telling you is that, hey, bro, you are on the x-axis. That's what the x is telling you. It's any number on the x-axis and it's changing. So when we derive it, we'll just write x point to show you that you have derived that now. It's no longer just x. It's no longer the x coordinate. You have derived it. The same thing for y. You just write y point, the derivative of y par rapport au temps. You just write y point. Same thing for z. You just write z point. And your vector vitesse is going to be x point suivant y plus y point suivant j plus z point suivant k. That's it. That's your vitesse in the coordinate Cartesian. The coordinate Cartesian is very simple. As I told you, there's nothing special to it. It's obvious stuff. It's direct stuff. You derive, it's just going to be x point, y point, z point. And when you derive again, it's going to be x dot. You just put 2 dots to show that you've derived twice. You put another, if you derive 3 times, you just put 3 dots on top of it to show that you've derived thrice. That's it. Rien de compliqué, rien de spécial. Je sais c'est nouveau, mais that's just the concept. That's how it is. It's x point, y point, z point. Then you've derived them. You derive them once, you just put 1 dot on top. You derive twice, you put 2 dots on top. You derive 3 times, you write 3 dots on top. That's it. Is it clear, Alpha? Okay, silence. So take it as it's clear. Then the vector vitesse, the magnitude of the vector vitesse, as I told you, you just square all its components and get their square root. So here we have the components of the vector vitesse as x point suivant y, y point suivant j, and z point suivant k. So you just square the x point, the y point, the z point, you square them, and you get their square root, and that's going to be your magnitude. Rien de spécial, rien de nouveau. We already did the vector magnitude. You just square, and you square root the entire expression, and you have your magnitude as that. So we go to the last thing we'll do today. It's 14 hours, just ask for 10 minutes of the time. It's just that we are racing against time. So it's better we do this. The coordinate cylindric. We'll try and do it in 10 minutes. We'll end at 14:10. Le point M est rapporté à la base RE, EFI, and K. And we know OM. We did this yesterday. OM in the coordinate cylindric, it was equal to, when we said OM, it was equal to OM prime plus MM prime, like that. We went like that from there to there and like that. And then we got our expression for OM as a rho, euro plus ZK. That was our expression for OM, rho, euro plus ZK. Okay, and we know that the vitesse or the velocity is simply la dérivée of the vector position par rapport au temps. So it's going to be d de OM dt. So V égale à d de OM dt. So we are going to derive this expression. But here, rho and euro are not fixed. They are all mobile. Okay, they are all mobile. Z is also mobile. Z is changing, but K is fixed. Remember I told you EGK, they are fixed. So the K, we'll just leave it out. So rho and euro, they are a product here. So we'll use the product rule. Calculus again. I emphasize, if you haven't done calculus, do it. So the product rule, we know that we derive one, leave the other one, plus you leave the first one and derive the second one. So it's going to be d de rho dt euro plus rho, we leave rho, d de euro dt plus. Now we derive this one, it's going to be d de z dt suivant k, because k is fixed. Sorry, I know you're tired. Just that I really want us to finish in time. I want to finish with this with you guys. So it won't take long. We're just going up to just this point here. Just explaining up to this point, and that's it. We'll be done before that. And we've done most of it, so don't worry. So we're going to begin with d de rho dt. Remember what I told you about x, y, and z. X is telling you it can be anything on this x. Y can be anything on this y. Z can be anything on that z. So when we derive it, we just put x point, y point, z point. For rho, it's the same thing. Rho can be anything on this line. We don't know what it is, but it can be anything on that line. So when we derive a rho, we're just going to write a rho point. We just put a dot on top of rho to show you that you have derived it. It's just going to become a rho point with a point on top. And then when we derive de rho dt, we do not have the expression for euro in terms of time. We do not have it. So we cannot derive directly with respect to time because we do not have the expression for euro in terms of t or in terms of time. So what we're going to try and do is we are going to compound the derivé. I'm sure you guys, you did this, the composé, derivé composé, the one for dy dx is equal to du dx over du over dy du. Sorry, it's dy du times du dx. This is what we're going to do here. We're just going to we're going to make it composed. So we say de rho dt. We're going to try and decompose it. So our expression for euro, when you look at your expression for euro in this one here, euro has been written in terms of phi. You see, it's euro equal to cos phi, sinus phi, cos phi, sinus phi. That means you can derive it in terms of the angle phi. So what we are going to do is we are going to compose or decompose this derivé by saying d de euro dt is going to be equal to d de euro de phi times d de phi dt. We haven't changed anything because this and this can simplify. It's the same thing, we have just decomposed it because euro has been written in terms of phi. So we can derive it properly with respect to phi. So after we decompose it like this, d de phi dt, again, you're just going to write phi point, simply, like rho point, x point, y point, z point. When you derive d de phi par rapport au temps, it's just phi point. And then d de rho de phi is what we were from looking at. We said when you derive rho par rapport à l'angle phi, it's going to give you e phi. So finally, your expression is de rho dt, which is a rho point suivant heureux, or rho point suivant heureux, plus this rho times phi point, this phi point that we found here, and the e phi that we found here. So it's going to be rho phi point e phi, plus this one here is going to be z point suivant k, and that's going to be your speed, your vitesse. I know you are tired and you have gotten maybe 5% of what I've explained here. So you revise, you try and go through. We have until Tuesday next week for you guys to go through all this. The tricky part here is just this part here where you decompose heureux, because heureux has been expressed in terms of phi, not in terms of t. So you cannot derive it par rapport au temps because you don't have the expression for it with respect to time. So you are going to decompose it. You say de heureux de phi because it's been expressed in terms of phi, and then you say de phi dt. And de phi dt, we can simply calculate it, it's just phi point. And then now we can calculate de heureux de phi, which is going to be equal to e phi, as we already saw in what I was explaining prior to this. People are tired, so I'm going to end here. We are going to continue next week on the vitesse spheric, then we'll go into the accelerations, and hopefully we'll finish these things next week, inshallah. This was our lesson today. Don't forget to revise. Make sure you revise. If you learn and you put the things aside, you will forget them. You learn them, you go through them twice, thrice, they'll stick in your mind. Are there any questions?
Yes, question.
Yes.
I've forgotten the meanings of M over R.
The meaning of what?
M and R. What are we? How are they working?
C'est le
Yes.
point matériel M and le référentiel R.
Oh.
So you say la vitesse du point M dans le, not référentiel par repère, la vitesse du point M dans le repère R.
D'accord.
Yeah. I did not mention this. Thank you for the remark. It's le point M. We're studying le point M dans le repère R. So you say la vitesse du point M dans le repère R.
Thanks.
Okay, you're welcome. Juan has said they've gotten 2% from what I was explaining. If you go through it, you'll get at least more. I know you guys are tired, so if there are no questions, we can end here. Are there questions? Okay, silence. Silence is golden, means there's no questions. That being the case, je vous souhaite une très bonne journée et un bon weekend, and I hope you guys are going to go through what we've done. All the best in your other classes, and it's au revoir from me. À la semaine prochaine, Inch'Allah.
Inshallah.